Okay, welcome in Fribourg. Uh, the, let's start this series of seminars. The first speaker is Gabriel Pallier, postdoc here in Fribourg. He's going to talk about cone-equivalent nilpotent groups with different Dehn functions. Please, Gabriel, thanks.
Hello everyone, thank you for having me here. So this is a joint work with Claudio Eisenberg and Romain Tessera. So I will start defining the words in the title, and I will go in reverse order. So I will start with the Dehn function, and after I will talk about the asymptotic cone. So the basic idea is that those are two large-scale invariants and that they give different information, in fact. So first, about Dehn functions. So for the whole talk, we will consider simply connected Lie groups. So let G be a simply connected Lie group with dimension at least 2, and you endowed with a left invariant Riemannian matrix. And the choice will not really matter, in fact. So examples that you can think of for the rest of the talk, you can think of RD. You can think of the Eisenberg Group. So the Eisenberg Group is a group of upper triangular real matrices. So and with the algebra. So they are, it is spanned by 3 vectors, and I will use a diagram to symbolize the Lie algebra, writing that there are 3 vectors and that their brackets is x3. So it's spanned by x1, x2, and x1, x2 is equal to x3. There is another group that will be important for the following. This is the Fidiform Group of dimension 4. So this can also be realized as a group of upper triangular matrices, but it's most important that you recall the definition from its Lie algebra. So this is this group, so it's also nilpotent. So, and this time, if you look at the Lie algebra, it's of class 3, in fact. Okay, so the non-zero brackets, they are 2 non-zero brackets, which are x1, the bracket of x1 with x2 is equal to x3, and the bracket of x1 with x3 is equal to x4. So this is so the Eisenberg group is nilpotent of class 2, and this group is nilpotent of nilpotency class 3. Okay, it's important that we have at least one example of nilpotency class at least 3 to illustrate what I want to talk about. And so last example, you can think of the group Sol mostly as a non-example for what I will say actually. And this is defined as the group, still a group of matrices e to the t, e to the minus t, x and y. Okay, so this is solvable, but is non-nilpotent. Okay, so for the rest, you can think of these groups. So now I want to define the Dehn function. So definition. So the Dehn function this is a function that goes from the half line to the half line and is defined in the following way. So this is the supremum over the loops gamma that goes to the group with length at most r. Okay, so you assume that they are rectifiable and they have length at most r of the filling area, which is defined as the infimum over all the disks such that the boundary, so this is a filling of the loop and we want the area of the disk. Okay, so you think this is a sort of minimal isoperimetric function. So we want to look at all the loops that have a given length and look at that filling area, understand which are the loops which are the hardest to fill, and this we make into a function that sort of computes the hardness of filling loops in the group. Okay, so I've said it's a talk about large-scale geometry. So this function is interesting and its fine behavior is interesting in itself. But for today, we will not care about the fine behavior because we want to look at this as a quantity, as a large-scale invariant. And I will explain what this means. But so I explained the equivalence relation that is relevant for the Dehn functions. So for two functions f and g from the real line, the half line to the half line. So I will say that g dominates f if there exists a such that f over is smaller than this. Okay, say that they are equivalent if each other dominates the other. And okay, and f okay, so for instance, if you take a and b, so a greater than b greater than 1, you will have n to the a smaller than a log n smaller than n to the b. And notice also that for any lambda, you will have e to the r, which will be equivalent to e to the lambda r with this definition. Okay, so now the property. So they are, I will state two properties actually. So one is the quasi-isometry invariance. So
maybe
yes.
You need like b is strictly greater than alpha, or am I understanding that?
Yes, sorry, yes, strictly greater. Thanks.
But also the other way around, or the b must be bigger.
Yeah. I just got okay. Okay. So
it could be small.
If G and G prime as above are quasi-isometric, okay, so quasi-isometric, I'll briefly recall what it means, but most of you must have met this definition already. So it means that there exists a function, so phi from G to G prime, and there exists lambda greater or equal to 1, such that for all x prime in G, 1 over lambda x prime minus c and so this is one thing, and the other is that for all y in G prime, there exists x in G such that d of phi of x y is smaller than c. Okay, so this is the pertinent comparison for large-scale geometry. So if G are quasi-isometric, then the Dehn functions of delta G and delta G prime are equivalent. So in particular, the Dehn function does not depend on the Riemannian metric that I put on the group. Okay, so this is the first property, and the second one is that, so it's a different definition, and the equivalence between both definitions is not so obvious, but so I state this here as a property. So if gamma is a compact lattice in G, then gamma is finitely presented and we could define the Dehn function in a combinatorial way, and if so SR is a finite presentation, we can define this is the following way. So for omega a word in the free group over S, we define the filling of omega as the minimal k, so minimal k such that omega can be written as a product from I equal 1 to k of conjugates of the relators okay, and then the Dehn function of gamma is the supremum for omega with length at most n of the field of omega, and this is actually the Dehn function of G. So this is a combinatorial analog, and for certain property it's more useful, it's easier to use this definition. So I just state some facts now useful for the following.
What is F sub S?
Is the free group over S. Okay, so this means that gamma is a quotient of free group over S by the normal closure, and so we write omega as a word. This is a word in the free group, but yeah, sorry. So I forgot an assumption. So omega represents 1 in gamma. Otherwise, it's not closing. So okay. So actually, the relevant. I should assume that omega is in the normal closure of R. Okay. So some facts. So for first, I will discuss for the group that I introduced. So examples. So for RD, it's n square. I assume that d is greater than 2. Okay, so this is for R2. This is like the isoperimetric inequality in the plane. For the Eisenberg group, this is R to the cube, okay? This is somehow more involved. So I will just sketch a quick proof for the lower bound, and actually the upper bound is often more involved because you have to fill all the loops, while for the lower bounds you only have to find one loop which is hard to fill. So I want to say that the filling in the Eisenberg group is at least R cube, and the loop that is hard to fill using the coordinates x, y, z here is the following one. So we take x, y, and z, and we take a loop which goes to n 0, 0. And n0 n square, and after so it's n square, 0 n square, which goes back here to 0 minus n square. It goes and then back here. So this was minus n square, and this was minus n 0, 0. And actually, if you project on the YZ plane, with the standard Riemannian metric, the most standard that you can put on the Eisenberg group, which makes orthonormal the standard basis, you will find that it decreases area, and if you look at the projection, it will be a triangle that encloses an area which is of the order of n cube. Okay, so this shows you that this loop needs a cubic area to be filled. Okay, if you project in this direction, you will reduce the area. It's not true if you project in the xz plane, but it's valid if you project in the yz plane. You will decrease area and find an area that it is of the order of n cube. Okay, and this loops has length 8n, I think. Yes, length. The length is smaller or equal to 8n. So we show this way that delta of Eisenberg is greater than something like constant times n cube. Okay, and conversely, it's more involved, so I keep it for the end if I have time. But this is only for the lower one. It also shows you, it already shows you that it's different from R3, for instance. Okay, so for L4, it happens that it's n to the 4. And in fact, there is a general bound, upper bound on the Dehn function, which is by the nilpotency class. Okay, so is of the order of F4, and more generally, so this is a theorem. More generally, if G is C nilpotent, then the Dehn function of G is bounded by n to the C plus 1, but there is no equality in general. This is a theorem. So it was stated and proved in some generality, which is not the full generality, but for us it doesn't harm too much. So it was stated by Gromov in 93, and then Gersten, Holt, Riley proved it in 2002. Actually, this was not a full proof in the whole generality, and they gave a full proof of. Okay, so for the Eisenberg group, you see that this is exactly this bound that occurs, and for the abelian RD as well. But for instance, for the 5-dimensional Eisenberg group, the Dehn function is n squared. So So this is not always, the bound is not always at, this bound is not always at 10. But this is the first upper bound that we can put as on a nilpotent group. And the last example is Sol. So just to show the difference, then the Dehn function is exponential. Okay? And this was proved by Epstein and Thurston in the book on automatic groups. Okay, this is my first part. Is there a question until now? So I've defined, yes?
Was there a natural counterexample for the other inequality failing with the nilpotent, because your point was that solve?
Yeah, I said it, but I didn't write it. So the counterexample is the 5-dimensional Eisenberg group. So x1, so it's 2 z y1. This is this group. So it's nilpotent of class 2, but still it has a Dehn function. So this for G, this group, this is quadratic. And if I have time in the end, I can spend some time to explain the difference between Eisenberg 3 and Eisenberg 5. Okay. So this is about the Dehn function, and now I will talk about the asymptotic cone. Okay, so the idea is to zoom out on G. And the question is, what do we see in the limit when we zoom out infinitely? Okay, so if G is Rd, it happens that in fact it has metric dilations. It means that it's isometric to its rescaling. So in fact we see Rd, okay, because it has metric dilation. So nothing happens. But we can ask the question for more general groups. So the notion of limit here is a bit subtle. So I will not enter full details, but for the groups with polynomial growth, there is a notion of limit which is more reasonable than in general, which is the Gromov-Hausdorff pointed Gromov-Hausdorff convergence. So I will discuss the case of polynomial growth now. And for this case, there is a theorem by Pensu which describes the result. So I will state the theorem now. So in fact it's due to Pensu, and there is a small improvement due to Breuillard, because what I will state is the combination of both. So if you assume that G has polynomial growth, so for instance if it's nilpotent, it has polynomial growth.
Does polynomial growth refer to the growth of the Dehn function here?
No, growth refers to the growth of balls in the group. Okay, so it's different. Yeah, it's the volume growth. Assume that G has polynomial growth. Then there exists a simply connected nilpotent group G infinity. Okay. I will continue on another board. Such that, okay, for all greater than 0. If you look at the ball centered at the origin of radius, so you look in G, so I should call the origin 1, of radius S to the N, and you renormalize the distance by N, you will converge in the Gromov-Hausdorff, pointed Gromov-Hausdorff sense to a metric space, which is the ball of radius 1, so of radius S in the group G infinity with a distance that we call the Carnot-Karateodori distance. So it says that in general for a group with polynomial growth, you will see something in the limit, and what you will see is still a group with a metric which may be non-Riemannian. So in the abelian case, it doesn't change anything. G infinity is the group itself, but in general, so D infinity is so it's a non-Riemannian, but still it's locally compact, and so okay, so it's a non-Riemannian. Locally compact, proper left invariant metric. Well, I will not need properties of this distance for today, so I will not enter too much into details, but this is still a metric space on which much analysis can be done. Okay, and so okay, so but what is important for me today is what is this group G infinity. Okay, so I said that in the abelian case nothing changes and the group is the same, and it's not true in general. In general, the Lie brackets may change a little. So moreover, so I will assume that G is nilpotent, but this is not a very serious restriction, but G infinity is built from G in the following way, and I will illustrate on an example. Okay, so you take the Lie algebra. So let G be the Lie algebra of G, and you set G infinity for first as a vector space. This is the direct sum for a greater than 0 of the quotient of the derived central series. So for me, C1G is G, C2G is GG, etc. Okay, and with the induced bracket, so you may know that with help of this is a little exercise in the algebra. The Lie bracket of a vector in Cij with Cig with a vector in Cgg is in Ci plus Gg. So you can induce Lie brackets. So with the induced Lie brackets in a way that you keep a Lie algebra structure, but some typically the Lie algebra structure may be slightly different than what it was before. So I illustrate on an example. So okay, if so this will be the Lie algebra of the new group. So I illustrate on this example. So I will call G43 the following group. It's taken from, you take a copy of the group L4. So it's defined with these brackets if it's of nilpotency class 3. And you take an Eisenberg group and you glue them in this way. So Y1, Y2, X4 will be an embedded Eisenberg group, and X1, X2, X3, X4 will be an L4 group. Okay, so if you compute there, so C2G will be just x3, x4, and C3G will be just x4. Okay, so when you define the new law, actually, and you look at the image of the y1 and y2, their brackets in the new law will vanish because it's 0 modulo. It does not have any component along the second. The x3. Okay, so G. The group at infinity is this one. So it's almost the same. But this bracket disappears. Okay, so this bracket is killed. So it's isomorphic, in fact, to L4 direct product with R2. Okay, so in fact, in general, what we performed here is maybe called the Algebra Contraction, and it simplifies a little the structure. And so here you get something which splits as a direct product. Okay, and okay, so the Dehn function of this one is not too hard to compute because we know the Dehn function of L4. So actually L4 has a model which is kind of nice, which is a jet space, and so in this kind, it's kind of so we know that here the Dehn function of a direct product is the maximum of the Dehn function of its summand. So the Dehn function of this group will be n to the 4. Okay. So okay. Alors, and so also property that sorry, excuse me. I want to state another theorem which is due to Pensu and which is kind of important, which is that if T and G prime are quasi-isometric, then G infinity and G prime infinity are isomorphic. Okay, so this looks very strong. And the idea is, okay, you will take the asymptotic cone. You know that in the abelian case, you get a Euclidean space. What will the quasi-isometry the quasi-isometry in the asymptotic cone will become a bilipschitz homeomorphism because the constant C that I wrote will become 0 if you want. So you will get a bilipschitz homeomorphism between two such groups, and there is a sort of Rademacher theorem which says that this is differentiable in some sense that gives you a group isomorphism between them. Okay. So this is especially this is a very strong quasi-isometry invariant. So the philosophy here is that we want to compare the two quasi-isometry invariants, the Dehn function and the asymptotic cone. So since this is a metric space, it looks like it has more information than the function. So what the natural question is, what the asymptotic cone tell us on the Dehn function? And it tells something.
So can I ask a question? So is it true that if you zoom out on the Heisenberg, the asymptotic cone of Heisenberg group, that should give just R? Is that just R2 or?
No, it's Eisenberg Group itself.
Okay.
Yes, because the Eisenberg Group has metric dilations, in fact. Okay, it's a Carnot group. I didn't say the word, but so when you apply this to a Carnot group, you get a Carnot group. So this is a Carnot group.
So the asymptotic cone in this example is the G infinity, is that correct?
Yes, always. This is a theorem. Yes.
associated graded group or something?
Yes, exactly. It's the associated graded for the gradation, which is the lower central series. So the first thing we can say, so this is actually not too hard. This was observed by Gromov, who introduced the whole asymptotic cone thing. If the asymptotic cones of G are simply connected, then is bounded by a polynomial.
What are the assumptions on G?
It's a simply connected Lie group. Okay. So the key fact is that if the asymptotic cones are simply connected, you can take a loop of length n and you can decompose it in a finite number of loops of size n over 2. And then you bootstrap on this, and inductively you will find that it's polynomially hard to fill it. So for instance, the nilpotent group, they fall into this category because the G infinity is a Lie group. It's very nice. It's completely simply connected. In fact, we already saw that then the Dehn function is bounded by n to the power c plus 1. So, elaborating on this, Papasoglou, so we took the argument of Gromov, but more carefully. So it's around 95, I don't know exactly. So let G be a nilpotent, simply connected nilpotent group. So if the Dehn function of G infinity is smaller than r to the power alpha for some alpha greater than 1. So in fact it then sorry, for all epsilon greater than 0, the Dehn function of G should be smaller than r to the power a plus epsilon. Okay, so this relates the Dehn function of the asymptotic cone. How hard is it to fill the loops in the limit with the Dehn function in the original group? So for instance, the nilpotency class is preserved when you go to the asymptotic cone. So starting from the proof I told about, the proof of Gromov, that the Dehn function of nilpotent group of class C is bounded by r to the power c plus 1, and using this theorem, you can get not exactly c plus 1, but almost for all nilpotent groups. Okay, so using the Dehn function of the asymptotic cones tell you something about the Dehn function of the original group. And so here our result is that this is optimal in some sense, because we cannot go in the other direction. So this is the theorem we prove. So let C be greater than 3. There exists, so it's a family of examples, in fact. There exists simply connected, and I will give some example. Nilpotent group G such that the Dehn function of G is n to the c, and the Dehn function of the asymptotic cone is n to the c plus 1. Okay, so the Dehn function will see the difference between both groups, while the asymptotic cone doesn't see.
Sometimes you write R, sometimes you write N.
Yeah, sorry, it's R, it's the same.
I have a question.
Yeah, sorry, it's R.
In Gromov's theorem,
Yes.
if I take the hyperbolic disk, the asymptotic cones are trees, right? So they are simply connected.
Yeah, and it's linear, the Dehn function.
Okay.
Actually, if the asymptotic cones are 3, then the group is hyperbolic and the Dehn function is linear. But this is not the kind of group that I will look at.
Instead, in Sol,
in Sol, it's interesting. So in Sol, Sol is, you can embed it in H2 times H2, and it's like a hyperplane. You have two Boltzmann functions, and so yeah. So Sol, the asymptotic cone of Sol will be of dimension 1, but not at all a tree. It will have incountable fundamental group. So it's not at all simply connected. Yes?
Yeah, I'm sorry, but I'm confused because you get C plus 1 here, but in the previous theorem, shouldn't be A minus 1? I don't see.
Where?
Yeah, like here.
that was R plus epsilon. A plus
A plus epsilon.
Yeah, but I'm confused because, like, in the second theorem, you get a C and C plus 1, like C plus 1 for G infinity and C for G. And here it was just plus epsilon. I mean, maybe I'm just, maybe I just don't see that.
No, this is sort of converse. This goes the other direction. There is no contradiction between both, no?
Okay.
Are we okay?
Yeah, I just have to think about it maybe because.
It says that the Dehn function of G is kind of smaller than that of G infinity.
Right.
But the question was, can it be strictly smaller? And this we prove it can be the case.
Oh, okay. Oh, yeah, because because it's
Okay.
small. Oh, yeah, now I see it, because it's not equivalent.
Mm.
Okay, sorry.
Yeah, it's not an equivalence here.
Yeah, sure.
Okay.
Just a technical question. Right, so G infinity is always equipped with sub-Riemannian metric, and so there you take like a coarse isometric function. I mean, what is the area? How do you measure area of disks in there?
You
In
put
G
a
infinity.
put a Riemannian metric.
So you take. Okay. So in G infinity you don't work with D infinity.
No, I had to write it because I had to write a theorem quite
Okay. So you
precisely,
still use a Riemannian.
it's really the Dehn function of G infinity.
Yes. Okay.
Also, in Gromov's theorem, you said you used the plural, right? As asymptotic cones are simply connected.
Yes, that's because when G is not of polynomial growth, there might be difference. Okay, so in fact it's a subtle issue. If you assume the continuum hypothesis, then for all Lie groups, there is a unique, as it is unique up to bilipschitz homeomorphism. But in general, they can be different with the general definition that I didn't give. Okay. So the first example is actually the one that I already wrote on the board. It's this one, because I said that the Dehn function of the asymptotic cone is r to the square, but actually the Dehn function of the original group is r to the cube. So the lowest dimensional example is 6-dimensional. Lowest dimensional example. This is with C equals 3, and it's the group G for 3. So I recall okay, it has, so this is the brackets, it has a cubic Dehn function, while its asymptotic cone has a b quadratic Dehn function. So while okay, and there is a corollary to that, which actually was already known in this example. It is that G for 3 and its asymptotic cone are not quasi-isometric. Okay, so, and it was already known on the example, because if we compute the Betti number, one is equal to 6 and the other to 7. Okay, and actually Shalom in 2004, the Betti number are quasi-isometry invariant. So there is some point of comparison here. One basic question, which is still not resolved, is to classify nilpotent groups up to quasi-isometry. And the big conjecture is that if two nilpotent groups, simply connected nilpotent groups, are quasi-isometric, then they should be isomorphic, in fact. This we know for Carnot groups because of Ponce's theorem. And afterwards, we can look for other invariants. So Shalom produced some, because in general, the Betti numbers of the associated graded are greater than the Betti number, greater or equal than the Betti number of the original groups. And so this is an invariant which is not at all obvious, but it's kind of sort of easy to compute. And so the difference with the Dehn function is that it's kind of simple to see that it's a quasi-isometry invariant because it has a geometric definition. It's like an isoperimetric function, but it's hard to compute. Okay, and so in this case we get we confirm this on those examples. Okay, so I will not say more in this direction because I want to talk about the centralized Dehn function. This will be my last part. So I will discuss how we obtain lower bounds on the Dehn function. And so actually our theorem was triggered by this example. This example was spotted by Yves Cornulier, and he suspected that something like the theorem could hold for the example because he computed a lower bound for the Dehn function of this group, which was cubic, whereas it should have been quartic. So it was intriguing, and he sort of believed that the Dehn function should be lower than expected, and that's why we investigated this group. So so this is my so last part. Yeah, so 3 centralized Dehn function and Dehn function. So I only explained on one example, the Eisenberg Group, how we did obtain lower bound on the Dehn function. But in general, there is a method that is in the following proposition. Okay. So I will take a central extension between nilpotently groups. So says that it is P nilpotent if here the inclusion of R sits in the piece term of the lower central series. Okay? And the proposition is that by looking at those sort of extensions, you can detect a lower bound on a Dehn function. Okay, so I will give one example. For instance, if you take the Eisenberg group, so you take Eisenberg group, and you go to R2, you go to 1 where this is the abelianization. Actually, you take the Z component goes to the Eisenberg group. This is a 2 central extension. Okay, and so the other one I can give is is 3 central because you add a bracket. So I recall the structure of L4. So you add an Eisenberg group and then you add a central extension. So this will be a central element because it commutes with every one, and you add it in the third term of the lower central series. So it's 3 central. And the proposition is that if G has a P central extension, then
Before you call it nilpotent.
sorry?
Down there to be P central.
Sorry, yeah, P central. Okay. Yeah, it's also called P nilpotent. Central. But yeah, we use we say P central. So P central extension, then the Dehn function of G is actually greater than R to the P. Okay, and there is a case of this which is kind of sort of known. It's about the Eisenberg group. If you met the Eisenberg group and someone explained you about the geodesic in the Eisenberg group, so the geodesic for the Carnot-Karateodory metric, they project like circles on the abelianizations, and this is because being a geodesic for the Carnot-Karateodory metric is being extremal. Is equivalent to being extremal for the isoperimetric problem in the abelianization. So the abelianization is R2 and it has a central extension which is the Eisenberg group. And so it's sort of the same to say that the Dehn function of R2 is quadratic and to say that this central term in the Eisenberg group is quadratically distorted. Because to each loop in the abelianization, you will associate a loop in the Eisenberg group which does not close anymore, but which reaches an element which measures the area that you have projected on the abelianization. So this is a more general principle, and this is a kind of general way to get the Dehn function, because this is not too hard to compute, because the central extension you can describe using the cohomology, and so this is completely computable, what is the maximal P central extension that you can have. And so there is a function which is called the centralized Dehn function of G. It is Rp by definition for maximal P such that there exists a p-central extension. Okay, so for the Eisenberg group, there is a 3 central extension, so the Dehn function is at least n to the cube. And for the 5-dimensional Eisenberg group, I said that the Dehn function is quadratic, and indeed you can check by computation if you want that there is no 3 central extension. There is a 2 central extension, which is the complex Eisenberg group seen as the complex 3-dimensional Eisenberg group, so it's 6-dimensional over R. But it's only 2 central. It's as nilpotency step class 2. So what happens that one difference between the 3-dimensional Eisenberg group and the 5-dimensional Eisenberg group is that the latter has no 3 central extension, and in some sense this is why his Dehn function gets lower. And so the group G43 that I wrote has a structure which is kind of reminiscent of the 5-dimensional Eisenberg group. It is what we call a central product. So this is a property that we exploit in order to show that the Dehn function is lower than expected. Okay, so how much time do I? Yeah, I don't have much time, so I will just state a bit of history on this subject. So there was a question which appeared like something like 10 years ago. Question by Young. Does there exist a G such that the central Dehn function of G is not equivalent to the Dehn function of G? And this was solved by Wenger. So answer is yes. So Wenger in 2010, he actually produced groups of class 2 with lattices. So there exists groups of class 2 such that the Dehn function is actually, so it's smaller than n squared log n, and it's strictly greater than n squared, so it's in between. Okay, and so actually the centralized Dehn function is always a polynomial with a round integer. So this is sorry, this is R. So okay, so they are not equivalent. But still, so there was the question: does the centralized Dehn function prescribes the polynomial exponent of growth of the Dehn function? And the answer is no. So we have examples where the Dehn function and the centralized Dehn function are differ by an exponent. And so this I will so this will be my the last result that I state. So this is still so now for all so it's for even c greater than 4, but actually possibly the even restriction is not serious, just that this is only thing we can prove. There exists simply connected nilpotent group with so this time the Dehn function is R to the C, but the Dehn function, the centralized Dehn function, is r to the c minus 1. So they really differ. It's really bad. Okay, they really differ by an exponent. So this lower bound, which is given by the p-central extension in a kind of algebraic way, does not always give the good exponent. And in fact, it is by using methods which are closer than the first one that I presented you that we can get better lower bounds. Okay. Whereas for upper bounds, we have to fill the loop themselves. So we have to identify which are the hardest to fill, and after we fill them in a combinatorial method, which employs a method which in fact were already to some extent present in papers in the Gersten-Rayleigh-Holt strategy and also in a paper by Olshansky and Sapir, who proved by combinatorial way that the Dehn function of the 5-dimensional Eisenberg group is quadratic. Okay, so I will stop now. Thank you.
Is it always true that the centralized function is more than the Dehn function?
Yes. Okay. In fact, I cheated a bit. There are equivalent definitions of the centralized Dehn function, and if you there is another definition which we give in the introduction of the paper, and it's much more simple to see that it's smaller than the Dehn function. Yeah, it's always smaller. But we don't know if it's a quasi-isometry invariant, this one.
And the G that you find in this last theorem, are they stratified group? Are they kernel group?
So no, they are not. They are of the same kind. They are produced by taking Fidiform groups and gluing the centers. And so for certain, so the Fidiform groups, the central extension of the Fidiform groups, there is something which depends on the class, and on the class mod 2, and this is why for when the examples are even dimensional, the associated grade, the group fails to have a central extension of degree exactly c. But still the Dehn function is of the order r to the c.
Is it correct that the central extensions, like the one you defined, they are in one-to-one correspondence with the one-parameter subgroups?
Central extension of, because when I say this is a central extension of R2, okay? So
okay.
they are in one-to-one correspondence with second cohomology classes, in the sense of equivalence of extensions. Do you have other questions?
There could be some a priori connection between Dehn functions and the ring of the group cohomology.
There is no a priori connection, but now we are investigating other groups. So so I erased, but regarding the classification of nilpotent groups after quasi-isometry, it's known that the Betti numbers are quasi-isometry invariant, but it was refined by Sauer in 2006, who proved that the real cohomology algebra are quasi-isometry invariant. And so there are 7-dimensional examples where the Betti numbers are the same, and we strongly suspect that the Dehn function might not be the same. But on these examples, the real cohomology algebra are different. So it's already known that they are not quasi-isometry. So it remains to investigate in higher dimension. On the other hand, computing many Dehn functions, it's not a very serious way to the conjecture. So perhaps there can be cases, but it will remain scarce.
So you just said quasi-isometric actually implies isomorphic real.
Yeah, this is a theorem by Roman Sauer in 2006. So yeah, the real cohomology rings are invariants.
More questions? Let's thank Gabriel again. Thank you, Gabriel.